the 5 d orbitals, okay, the dxy, dxz, dyz, and the dx squared minus y squared, and the dz squared. Here's all 5 of them situated in space relative to the x, y, and z axis. Do you see how they didn't take all 3 of them and superimpose them to show you what a d sublevel is, like they did up here? Because what would it look like? Just like a bumpy sphere, right? I mean, this looks like a bumpy sphere already. This would look like even more like a sphere that has bumps on it outside of it. Are you okay with this? Good. So again, these are the d orbitals situated about, if we put them all together, we would get a d sublevel. And maybe it's probably a good idea right now to draw the atom now as we understand it. So let's do that. Let's do that. I'll put it up over here. We know we have the first energy level, right? Here's our nucleus. First energy level, S sublevel. First energy level has an S sublevel, 1 orbital, an S orbital. It's spherical. There, I've drawn it. Now, the second energy level consists of 2 sublevels. There's the S sublevel with its 1 S orbital. I've drawn it. And now the P sublevel with its 3 p orbitals, which are arranged in space 90 degrees from one another along the x, y, z axis. So we have the 2p sub x orbital, the 2p sub y orbital, and the 2p sub z orbital, all making up the 2p sublevel. Now we have the third energy level. The third energy level consists of the 3s sublevel with its 3s orbital. It has the 3p sub x, the 3p sub y, the 3p sub z, and then it has the 5d orbitals that make up the third energy level. Can you see how this is going to start to look like a spirograph? You guys know what a spirograph is? Yeah, those of you who play with a spirograph. Yeah, do you see how it's going to start looking like? I mean, it's going to look, it might look sort of interesting and artistic, but it's going to be nonsensical in terms of trying to be able to look at that and really see anything meaningful. You guys understand? This is why we represent it this way. This doesn't give you a true reflection of how it actually looks, but it does show you, hey, these orbitals are degenerate, they're all equal in energy, the electrons belonging to them are all about the same distance on average from the nucleus. It's useful, and it shows you how the energy lines up from sublevel to sublevel. We good? If we go to the 4th building with its 4 floors, its 4 sublevels, we go to the S sublevel, the P sublevel, the D sublevel, and what's the 4th sublevel called? Level-wise? The F sublevel. The F sublevel, guess how many orbitals make it up? 7 orbitals. Okay, 7 orbitals. Of those 7 orbitals, we have the Fz cubed, the Fy cubed, the Fx cubed, the Fxyz, the Fz times the quantity x squared minus y squared, the Fy times the quantity z squared minus x squared, and the Fx, of course, minus the quantity z squared minus y squared. I do not expect you to know the letter names for the F's. Okay, so you do not have to know that. You should know that the F values, the M sub L values, range from what to what, Lance? M sub L.
M sub L equals -3.
All the way up to +3. Everyone understand how Lance got that? Okay, so you should know the M sub L allowable values, but I wouldn't expect you to be, you don't have to worry about negative. What I do want you to know is the shape of the orbitals. It turns out that of the 7, 4 of them are 8-lobed, and 3 of them are 2-lobed with a double torus, a double donut. Here they are, guys. Yeah, 4 of them are 8-lobed, and 3 of them are 2-lobed with a double donut. Now, look here, guys, because I'm going to pass this book around. If you want to take a look, here's the previous page we're looking at. If you want to take a second look at this stuff, and here's the F's. I do not look. I expect you to be able to draw S, P, and D orbitals. I do not expect you to draw F's. Okay, I'm not going to make you draw an 8-lobed orbital. Okay, so you don't have to worry about that. But you should know that 4 of the F orbitals are 8-lobed, 3 of them are 2-lobed with a double torus. And you can just pass that around, get a second look at this. The f orbitals are on the next page. Okay, so if you flip over. Questions at all? Yep.
How do you spell torus? The T-O-R-U-S.
T-O-R-U-S is the singular. T-O-R-I for if you want plural. Yeah, we don't say toruses, we say tori. Questions at all? All righty. Well, not too bad. It turned out, though, I mean, we thought we had this down at this point.
The model we're on.
Pardon me? No. It turned out we thought we had this pretty well up to this point. You're going to have to take some notes here because it's mentioned in the text, but it's not actually clearly defined for you. Schrodinger originally, when he solved this and treated the electron as a wave, saw that the electron from the mathematics was quantized, the electron was quantized with respect to energy in three ways, and we stipulated all three ways. You need to know about the energy level electrons and the sublevel influences it, and the individual orbital influences that. However, we ran into a physical phenomenon we couldn't explain called the Zeeman effect. And let me explain what the Zeeman effect is. Up here, guys. The Zeeman effect is, and if you look on page 13, it says required to account for the Zeeman effect. I don't tell you what the Zeeman effect is, but you need to know what it is. So let me tell you what it is. The Zeeman effect is the splitting of line spectra. Get this down. The Zeeman effect, so on page 13, in the middle of the page, under the fourth quantum number, I tell you the Zeeman effect. Here's what it is. It is the splitting of line spectra. The splitting of line spectra for some elements when they are excited in the presence of a magnetic field. The splitting of line spectra for some elements when they're excited in the presence of a magnetic field. Okay, up here. Splitting of line spectra for some elements when they're excited in the presence of a magnetic field. Now that's all well and good, but you got to know what that means. So let me explain what it means. All right, you know how if you do an emission line spectra like we did in class with the glasses, you know, we got the colored lines? All right, let's imagine up here, look up here, guys. Let's imagine you see one red line. Okay, so we're exciting something and you're seeing a red line. If you take that same element, with the same material, and you excite it, but this time you do it with a magnetic field around it. So we put magnets around this thing, so it's now in a magnetic field. What will happen for some elements is all of a sudden where that one red line was, instead of one red line, now all of a sudden there are two red lines on either side of where the original was. That's what I mean by the splitting of line spectra. You guys understand? Now, our model, as it stands, can't explain that. So we knew that we had to make an amendment to Schrodinger's model. If I ask you any questions about the Schrodinger model of the atom, though, you can assume we're talking about with the amendment. In other words, Schrodinger's model is as it stands today. And that is, we need a fourth quantum number. It became pretty apparent. Pauli is the guy who, just spelled like Paul with an I at the end. Pauli is the guy who's responsible for the fourth quantum number being added to the wave mechanical model of the atom. And it was added in order to account for the Zeeman effect. Now, how can we do this? Well, to be honest with you guys, if you push me and you take AP, I'll go into it and you'll have enough background information, you'll understand, and I can further tell you. If I try to tell you right now, I'm going to lose too many people. It's just not worth the time. We've got too much chemistry and we've missed too much school, so I'm not going to. So just take my word for it. Essentially what it means is this. The only way we can account for the Zeeman effect is if the electron is acting or behaving as a tiny little magnet, and it's interacting with that magnetic field we were putting it around. A charged particle, remember how I told you with the electric generator how it works? You spin it, the magnetic field causes the electron to start moving. If the electron is spinning, it'll set up its own magnetic field. You guys know about the Earth's magnetic field, right? Similar idea. It'll set up its own magnetic field, and that magnetic field can either interact in a constructive way with the magnetic field you're putting in. In other words, let's say they might attract each other. That would lower their energy. Or it could do so in a contrary way, where it's increasing the repulsion, in which case that would raise the energy. And that means we have two energy states that are possible. So we could have a line on either side of the original. All you have to know is this, is that to explain the Zeeman effect, the only way we can account for it is if the electron is acting as a tiny little magnet, and that means it has to be spinning. And this is why Pauli proposed the fourth quantum number. So we now have a fourth quantum number. Symbol is m sub s. It's called the spin quantum number. Its allowable values are m sub s equaling plus or minus 1/2. And it specifies the spin of the electron about its axis. Now, whether you say an electron spins clockwise or counterclockwise truly is a question of perspective. It's pretty much arbitrary. Most people can see what I'm about to ask you to try to look at, and where are you? I knew I had you in here. Perfect. Yes, that's what I need. Most of you will see what I'm talking about. There are some people who just don't see it. Don't lie to yourself. If you don't see what I want you to see, call me over, because this, in my hand, will allow you to see what you're having trouble seeing with what I'm going to talk about. I'm going to start talking about. Take your pencil. And I want you to go ahead and hold it in such a way as you're looking down onto the top of the pencil. Okay? And what I would like you to do at this point is, while you're looking down at it, I want you to spin it so that it's spinning clockwise. So you're looking at the top of the pencil and you can see it spinning clockwise. Now, watch up here first. Stop from spinning for a moment. What you're going to do is this. You're going to raise your pencil, keep spinning it clockwise. You're going to do that. And then I want you to look at the bottom of the pencil. So you're going to hold it directly above your head and look at the bottom and then tell me which way it's spinning. So you're spinning clockwise, you raise it above your head, looking at the bottom of the pencil, which way is it spinning? And what you should see is it's spinning counterclockwise. Now, most people see it, some people will not. Nobody see it? Okay, you see it? Anyone not see it? If you don't see it, it's because this will help you. This will help, because this is better than a pencil. You see it, Joe? Hunter, you see what I'm talking about? Anyone not see it? No one? That is a first, honestly. Seriously, everyone saw it? Okay. All right, so whether we say something is spinning clockwise or counterclockwise, you saw firsthand. Well, it depends on which way you're looking at it, right? All right, we have adopted a convention. By convention, spinning clockwise or counterclockwise, the first electron into an orbital, there's a consequence to this last quantum number. It turns out, when Pauli introduced it, that an orbital can only handle 2 electrons maximum. I don't care what type of orbital it is. It can be an F orbital, a D orbital, an S orbital. No orbital can handle more than 2 electrons. That's the most that can go into an orbital. It's sort of like saying the room's occupancy limit is 2 people. Okay? I don't care whether it's a big room that you've rented out or a broom closet. The most that can fit into that room, the most that can fit into any orbital of any kind, is 2 people, 2 electrons. Now, in order to have a stable arrangement, electrons repel each other, don't they? Yes? Okay. And because they're negatively charged. If they're spinning, they're going to be spinning in such a way to act as a magnet, right? Now, you know, you've played with magnets before. You can situate the magnets so they repel each other, right? Or you can situate them so they attract, which I suppose is a more stable arrangement. Attract. So in other words, the electrons already are at each other's throats. They're already repelling one another. If we can minimize that, one way of minimizing would be so that they're at least a little bit attracted because of their magnetic fields. They're still going to be repulsed overall. But we can minimize that repulsion. The way to do that is to make certain that we don't have 2 north poles together, okay, or 2 south poles. In other words, we need them to have opposite spins. And so 2 electrons belonging to the same orbital will naturally have opposite spins. It's just a more stable arrangement because it minimizes repulsion. The first electron to go into an orbital, so this is the convention I was talking about. The first electron to go into the orbital is assigned the m sub s value of -1/2. Okay? The convention is we always fill negatives to positives. So for instance, if I were going to put an electron into the second energy level, the second sublevel, P sublevel, these 3p orbitals all have the same energy. So does it matter which one I put it in? Well, technically, no. But by convention, we